Hello students, in today's video we will start our lesson Wave Optics. This is the 10th chapter of NCERT textbook, in which light is treated as wave. As you know, light in ray optics we studied as moving in straight line. We never discussed its wave nature over there. So ray optics is also known as the geometrical optics, in which light is considered to be moving in straight line, and it will change its directions when it falls on objects, or it is changing the medium. Sir Isaac Newton was a strong advocate of the particle nature of light, but the Dutch physicist Hans Christian Huygens believed that light was made of waves, vibrating up and down and perpendicular to the direction of propagation of the wave. And he visualized the light's movement as a waveform. In 1678, Huygens proposed that every point that a luminous disturbance meets turns into a source of the spherical wave itself. The sum of the secondary waves, which are the result of the disturbance, determines what form the new wave will take. This theory of light is known as the Huygens principle. Using the above principle, Huygens was successful in deriving the laws of reflection and refraction of light. He was also successful in explaining the linear and spherical propagation of light using this theory. However, he was not able to explain the diffraction effects of light. Later, in 1803, the experiment conducted by Thomas Young on the interference of light proved the Huygens wave theory of light to be correct. Later, in 1815, Fresnel provided mathematical equations for Young's double-slit experiment. Max Planck proposed that light is made of finite packets of energy known as light quantum or photon, and it depends on the frequency and velocity of light. Later in 1905, Feinstein proposed that light possessed the characteristics of both particles and wave. He suggested that light is made of small particles called photons. Quantum mechanics gave proof to the dual nature of light. Now we will discuss Huygens principle. Huygens principle says every point on a primary wavefront is in itself the source of spherical wavelets, which are called secondary wavelets, which spread out in the forward direction at the speed of light. The sum of these spherical wavelets form a phenomenon called wavefront. All points of a wavefront of light in vacuum or transparent medium may be regarded as new source of wavelets that expand in every direction at a rate depending on their velocities. The wave theory is a powerful method of studying the varying optical phenomena. If a medium is homogeneous and has the same properties throughout, meaning isotropic, permitting light to travel with the same speed regardless of its direction of propagation. So we can see here, this is a point source of light over here. At O, we have a point source of light, and light start propagating forward direction like this. And at a time, let us imagine this is the point where the light reaches, that is A, B, C, D, E, etc. So that as that points as origin, if we draw spheres, the tangents of them both in the forward direction as well as in the backward direction gives the new wavefront. So what you can call this A, B, C, D, E is a wavefront in which the light particles are vibrating in phase. After some time, it reaches A dash, B dash, C dash, D dash, E dash. There also, it will be vibrating in phase over these tangents of the sphere. If you look back, A double dash, B double dash, C double dash, D double dash, and E double dash forms and another wavefront, which is the tangent of the spheres again, the joint tangents of the sphere, the locus of all points which are in the same phase of vibration, gives a secondary wavelet. So if we consider each point of a wavefront uh, as a source, it can produce a forward wavefront as well as a backward wavefront. A surface tangent to the wavelets constitutes the new wavefront and is called the envelope of the wavelets. A wavefront is defined as a surface over which the phase of the wave is constant, meaning the angle will be the same. The angle of vibration of the particles of that medium will be the same angle. In a particular wavefront, at a given moment of time, all particles of the medium are undergoing the same kind of movement. Wavefront is also defined as the locus of all points having the same phase of vibration at a given instant of time. The shape of wavefront depends on the shape of the source of disturbance. For example, if we have a point source, the wavefront will be spherical in shape. If you have a line source like this AB, it will have a cylindrical wavefront. If the wave is coming from infinity, that is the source at infinity, will produce a plane wavefront like this. And one more thing, the ray of light is the perpendicular to the plane of this wavefront. So for example, here if you take, this is the wavefront, this rectangular plane is the wavefront, and these arrows over here shows the ray of light which are perpendicular, which are in a perpendicular plane to the wavefront. Even here also in the sphere as well as in the cylinder, the ray of light is perpendicular to the wavefront. Refraction based on wave theory, and we will derive Snell's law. So here, as in the figure, you can see different rays of light are traveling through medium 1 and it enters medium 2. Medium 1 and medium 2 are having different refractive indices. Say N1 we can take for medium 1 and N2 for medium 2, and from the figure it is obvious that N2 is greater than N1. That means N2 is a denser medium and N1 is a rarer medium because the rays of lights are bending towards the normal. So you can see NA is a normal here. FA is the incident path of the ray. AC is the refracted path of the ray. And what is AB? AB is nothing but the incident wavefront. Incident wavefront. Similarly, CD is a perpendicular to the refracted rays, so it is called the refracted wavefront. Okay, so the angle of incidence is the angle between the incident ray FA and the normal here. So that is called angle I. Similarly, over here by geometry, this will be also angle I itself. Similarly here, angle R, that is angle of refraction, that is the angle between the normal and the refracted ray AC. So geometrically, this also will be R. So here we have to find out the time taken by the rays to travel from the incident wavefront AB to reach the refracted wavefront CD. Okay, and all these rays takes the same time to reach CD from AB. So I will calculate what is that time which is required for the wave to travel from F to C. If you consider only this ray for instance, we will find out the time taken by the ray FAC. Okay, so what we do is time is equal to distance divided by velocity we will take. So let us imagine the medium 1, the velocity of the wave is v1, and in medium 2 the velocity of wave is v2. So time is equal to fa, the distance, divided by v1 plus ac divided by v2. Now what we have to do is we will find out fa and ac in terms of that angle I and r, as well as the constant distance of the interface called AD. We will consider a ray which is passing through PQR for the calculation of Snell's law. We will take the example of the ray PQR here. So we can say the ray PQ is incident at an angle I over here, and it is refracting through an angle R. So according to geometry, this angle is also I, this angle is R. Okay, so what will we do is we will find out PQ, the distance PQ and the distance QR in terms of that angles to calculate the time. So what is the time taken here for the ray to travel from the incident wavefront to the refracted wavefront? We have to calculate. That is, time is equal to distance PQ divided by the velocity V1 plus distance QR divided by the velocity V2. Now PQ, QR we will find out. PQ is the, see, the one of the side of the triangle, and the hypotenuse is AQ over here. Okay, then in this triangle APQ. So PQ we can find from the triangle APQ, in which we will say sin I is equal to opposite side PQ divided by the hypotenuse AQ. So we will put this equation numbers here, 1, 2. Similarly, we will find out what is sin R. Sin R is equal to, again, the ray and the wavefront are perpendicular. So this is the perpendicular angle. Sin R is equal to opposite side. Opposite side is QR divided by the hypotenuse. Hypotenuse is QD. Okay, that is our equation number 3. So we got PQ and QR. What is PQ? PQ is equal to AQ sin I. AQ sin I. Similarly, QR, to substitute in the time, we got it as QD sin R. Now QD is a variable distance because, as the rays are changing their positions, different rays, when you consider this QD distance is different. So what will we do is we will take it as AD minus AQ. So QD can be written as the constant distance AD minus the distance AQ into sin R, we will write it. So this is our equation number 5. Now we will substitute the values in the time equation. So time is equal to, we got PQ. PQ, instead of PQ we will write AQ sin I divided by V1 plus AD minus AQ sin R divided by V2. Now what we have to do is open the bracket of the second term. So we get it as AQ sin I, time is equal to AQ sin I by V1 plus AD sin R by V2 minus AQ sin R by V2. Sin R by V2. So you see over here AQ is a variable. Okay, AQ is a variable because as I told you before, the position of the rays will decide what is AQ has to be. So if you take a ray here, AQ's distance will change like this. or if you take a ray there, AQ's distance will change like this. So that means AQ is a variable. But do you know that the time taken by the rays, all these rays, to travel from the incident wavefront AB to the refracted wavefront CD is a constant. So LHS of your equation is a constant. Time is a constant. So in a constant LHS, if you have, you should not have a variable RHS, right? So what we have to do is this AQ containing terms you have to consider as equal to 0. So which are the AQ containing terms? This first term and the third term. That has to be made into 0. So since t is a constant, we say here we can say AQ sin I by V1. We'll write here AQ sin I by V1 minus AQ sin R by V2 has to be equal to 0, because the condition says t is a constant, so the right hand side also has to be constant. So but these terms containing AQ are not constants, so that the terms which are containing AQs, we have to make it into 0. So what we get is AQ sin I by V1 is equal to AQ sin R by V2. So AQ get cancelled. What we get? Sin I by sin R. Sin I by sin R is equal to V1 by, it's V1, okay, V1 by V2. So this is our equation number 5, I believe. Okay, sin I by sin R is equal to V1 by V2. What is V1 by V2? Sin I by sin R is also, we have studied, it is N1, N2 by N1, N2 divided by N1. So you learned like Snell's law. Sin I by sin R is velocity of light in medium 1 by velocity of light in medium 2, which is also equal to N2 by N1. So where is the wave theory we applied here is in this wavefront. Wavefront concept is something which is derived from the wave theory. The corpuscular theory or the ray optics doesn't have a wavefront concept. So here in this derivation, where we used wavefront, where we used wave theory, is the concept of wave front we introduced. So that is how, otherwise we can see like it is all geometrically proven like we feel. But actually this light is considered to be coming in the form of waves, even though we have drawn as straight lines. They are coming in the form of waves. They create a wavefront at a particular point of time called AB. Then they refract, the ray of light refract, and it forms another wavefront here at CD. So here all you can see that there will be a tangent drawn, like here for example there will be a tangent here, a tangent, a circular wave position will be there. It's tangent only we have drawn, and we have joined so that it forms a refracted wavefront. As well as here also we can see like they will be like spherical waves whose tangents are joined to form the wavefront called AB, incident wavefront called AB. So that is the place where we use the wave theory in this. Reflection of light can be explained based on wave theory. Reflection rules are like the incident ray, the reflected ray, and the normal lies in the same plane. And angle of incidence is equal to angle of reflection. So here in the figure, we have shown here the incident wavefront called AP and the reflected wavefront called A prime P prime or A dash P dash. So here the rays of light which are falling on this reflecting surface is reaching the other side, that is the on the reflected wavefront at the same time. All the rays which are, whether they fall on A, point A, or K or P dash, it all reaches the reflected wavefront at the same time. Now we will take a ray which is QK dash as a reference ray. QK is the incident path and KQ dash is its reflected path. So we will mark the angles of incidence and reflection on that. This is the angle of incidence over here. This is called the angle of incidence I, and this is the angle of reflection R. Now the time taken by the ray, as we saw before, it will be the same for any ray you take. So it will be like time is equal to distance by velocity we will take here. So let us imagine n is the medium refractive index and v is the speed of light in that. So t is equal to, we can take qk as the incident path divided by v plus the reflected path is kq dash divided by v. So this is our equation number 1. Now we will take this is the normal, this blue line is the normal here. So here we will find out the angles of incidence and reflection from these triangles, and accordingly we will calculate the time in terms of the angle. So we'll find out what is QK is from the triangle AQK. So in triangle AQK triangle, if you take in triangle AQK, sin I is equal to QK divided by AK. We'll put it as equation number 1 here. Then we will find out sin R as well. Sin R is equal to, sin R from where we will find is from the triangle KP dash Q dash. So from triangle KP dash Q dash, sin R is equal to, this is the perpendicular there. So sin R is KQ dash divided by KP dash. So what is QK? QK is AK sin I, and KQ dash is KP dash sin R. Now we will apply this in the time equation. That time equation is AK sin I by V plus KP dash. KP dash we will write like it is AP dash distance minus AK. So we will write like it is AP dash minus AK into sin R by V. Now what you have to say is this AK, the distance AK is a variable because it depends on the ray which is falling on it. So if the ray is over here, AK will be here, or if the ray is considered here, the K will be here. So AK is a variable distance, but time is a constant in the equation. The LHS is a constant, so as our RHS also, but AK is a variable here. So the terms containing AK we have to eliminate. So what we do is AK sin I by V minus AK sin R by V, we will take it as 0. So AK and V are the common factors in it, which will give us sin I is equal to sin R, or I is equal to R. So this is the second rule of reflection, that is angle of incidence is equal to angle of reflection. Here again we have proved this equation based on, or proved this law based on the wave theory, considering the concept of the wavefront. The A dash is the incident, AP is the incident wavefront, AP is the incident wavefront, and A dash P dash is the reflected wavefront. So wavefront is a concept of the wave theory. Based on that we proved the laws of reflection. I hope you understood the derivations of refraction and reflection based on wave theory, as well as the very basics of the Huygens wave theory, that is how is light explained in terms of waves. And we have to now onwards we have to think of light as having a dual nature. It has both particle nature and wave nature. Thank you for watching.